Welcome to Teja Statistics. In this statistics, we are going to learn about this efficiency. Okay, efficiency property in our theory of estimation we have in a class of consistent estimator for a parameter. There exists one whose sampling variance is less than that of any such estimator. It is called most efficient estimator. Efficiency is based on the variances of the estimators. Among the estimators, the estimator which has a minimum variance is called efficient estimator. Yeah, what is efficiency? Efficiency is nothing but it is a which one is having the less variance. Okay, yeah. If T1 is the most efficient estimator with the variance V1 and T2 is the any other estimator with the variance V2, then the efficiency is E is given by E is equals to V1 divided by V2. If it is less than 1, then we can say that V1 is less than V2. So which variable is the which estimator is the best here? Here T1 is the best because T1 is having the V1. Okay, the sample mean is the most efficient estimator than the sample median for large samples, say in normal population. So like that, most efficient estimator, efficiency of sample median compared to sample mean, expected value of variance of x bar divided by variance of median. So what is the formula for this? Sigma square divided by n, 5 into sigma square divided by 2n. We got the value as 2 divided by 5, that is 0.637. So next, the minimum variance for unbiased estimator. A statistic t equals to t of x1, x2, x3 and so on xn is said to be a minimum variance unbiased estimator of the population parameter of the t or theta. So here t is an unbiased estimator of theta. Second condition, the t has the smallest variance among all the other unbiased estimators of theta. So obviously expected value of the t equals to theta, and variance of t is always less than or equals to variance of t dash. Next, see some problems for understanding this calculation, okay, or efficiency. A random sample x1, x2, x3 and so on xi, x5, okay, of size 5 is drawn from normal population with the unknown mean and variance. Consider the following estimators to estimate the efficiency. So here T1, T2, T3 they given, and uh, here which estimator is the best they are asking you to find out. So in general what we have to do here is, here we have to do the uh, what we can say that we have to calculate the variances, okay, for T1, T2 and T3. So among these three, which one is having the less variance? Then we can say that that T that uh, estimator is the best estimator or efficient estimator, we can say. Let's see which one is going to be get. So solution for the given problem. So given the observations are x1, x2, x3, x4 and x5 are random samples drawn from the normal population with mean mu and variance sigma square respectively. So here we denoted that one. We are applying the variance for the t1. So first value is variance of any constant will get outside, then we will get 1 divided by that 5 will become 1 divided by 25, that is square of that. So variance of x1, variance of x2, variance of x3, and variance of x4 and x5, like that. If you add all these variances with the sigma square, then you will get 5 sigma square uh, divided by 25. 5 1 ja 5, 25, so that is 1 divided by 5, you got the 0.2 sigma square variance of t1. Next, consider the variance of t2. So variance of t2, which you have that x1 plus x2 by 2 plus x3. So the constant will become 1 by 4. Uh, variance of x1, variance of x2, but here the 2x3 will become the 2 will get the square, that is 4 variance of x3. So variance of any constant will become the square. Okay, so 1 divided by 4 of this 6 sigma square divided by 4, that will you will get the value as 1.5 sigma square. So this is the about variance of t2, the second estimator. Next, consider the third estimator, so which is already having the value as 0. Okay, in that value, so variance of 2x1 plus x2, if you apply a variance to that, then you will get 1 divided by 9, the square value. Okay, next 4 sigma square plus sigma square 5 divided by 9, that is 0.56. Among these three, t1, t2, t3, which one is less than? Very t1 is very less than, I hope so. So t1 we got as 0.2, t2 we got as 1.5, and t3 we got 0.56. So which we can observe t1 is the best among these, because variance of t1 is 0.2, and variance of t3 is 0.56, and variance of t2 is 1.5. Next, similar problems you have to do. Let x1, x2, x3, and x4 be an independent random sample from a normal population, such that so expected value of xi is equals to mu and variance of xi is equals to sigma square. So here also, if they given uh, yzt, so what is the efficiency value of y related to z and y related to t, they are asking you to calculate. So consider the variances of that estimators. So variance of y is equals to same, you got the values as 4 divided by 16, so that is 0.25 sigma square. Now consider the variance of z. So what is the z value they given? x1 plus x2 plus x3 plus x4 divided by 5. So that is 1 divided by 25 of 4 sigma square. So that is 0.16 you got. Okay. Next, on comparing the last but not least, the next t value. So 1 divided by 16, you got here 5 divided by 16 sigma square, so which is 0.3 sigma square. So on comparing this, which one is the best, you have to decide why is the best, because this y got as 0.25 and this z got 0.16. On comparing these two, z is the best. Okay, next, on comparing this y and t, so the t is having 0.3, so the y is the best here. Okay, very simple and easy to understand these calculations. Next, the most important topic, that is called sufficiency, efficiency and sufficiency calculations. An estimator Tn is said to be a sufficient estimator for the parameter theta if it contains all the information in the sample regarding population parameter. So let x1, x2, x3 and so on xn are uh, be a random sample of size n with the density function f of x comma t. Then a statistic t of all observations are said to be the sufficient estimator of theta if its conditional probability or conditional distribution of these two are independent of theta. So what they want to say here is the sufficiency condition plays a very important role. That is the conditional probability of statistic and the functional statistic and the joint probability function is completely independent. Okay, then only we can say that the xi or the theta is t is independent of theta. Then only we can say that the t is going to satisfy the sufficient estimator condition. Okay, let's see x1, x2, x3 and so on. X can be a random sample drawn from a normal population with mu comma sigma square. Then the population summation xi is said to be sufficient for mu, and summation x square is sufficient for sigma square. Okay, like that we have different calculations. Okay, up to this we are going to finish these things. Okay, we'll see and we'll continue with the same for the second year BSc data science and the statistics. Thank you.